Yesterday I was very worried because we had to do so much work for this seminar. But tonight I'm even more worried because I have to introduce Mike Yemolkowski, which is not an easy task for anybody. Anyway, to be diligent, since Mike about 3 years ago held the Croce lecture, which is one of the which is the most prestigious lecture in Italy, and he was introduced by a friend, a common friend, Professor Barla. I asked Professor Barla to give me the introduction, but I discovered that it was a 6-page introduction. So I don't think you tonight would like to hear 6 pages. If you wish, you just raise your hands. I think that the names like the Pisa Leaning Tower, the Venice Lagoon Rehabilitation, Messina Suspension Bridge, the Chernobyl Safety, you can extrapolate from this. They speak by themselves. Mike has delivered the scores of orations, received the quantity of academic prizes. He was elected the president with an astonishing majority. I don't think many of the presidents have had such large majority when they were elected. I think he's a top-level theoretician and practitioner. He's a highly positive character. He's charismatic. He aggregates. You know, people say to me, if you are Mike's friend, you are my friend. He generates enthusiasm. He is available and generous. He's a model for many of us. With him, we like to much to argue. Maybe we can argue tonight for KDVS and how many Saturday mornings by telephone we stayed 1 hour on the phone arguing. So we enjoy very much this. Mike can see 1 mile or 1 year ahead of many of us common mortals. I think we would not be tonight in this room if I had not had the luck to cross him in my life. Mike, please.
Thank you, Silvano, for this very friendly and touching presentation. The only problem is that after this presentation I feel even elder than I am in practice, because he was obviously exaggerating in describing my personality. We are friends from more than 40 years, and really we are interacting almost every week or every 2 weeks on phone, which make our wife, at least my wife, desperate, because we are talking for 1 hour or something like this. And something is, in meantime, she is preparing the lunch and something is going wrong in the kitchen. I am very happy and very proud that I have been invited to deliver this small presentation. I must express my thanks to Dr. Feltz-Metzger and to Professor Marchetti participating in this conference, in this symposium. I realized that the format of this symposium, the frame of this symposium is extremely well planned with respect to the problem to closing the gap between the theory and practice, which is one of the major problems of modern geotechnical engineering. My talk will be about a huge tiling pond in Poland, copper mine tiling pond, and you will see that this is a problem on which we are working since '92. I am saying we because you will see my friends, my colleagues involved on the international board of experts at this job. And despite this very long work and despite tremendous effort spent in site characterization, we have many unsolved geotechnical problems, and because this tailing is growing, the dam are risen every year the problem is causing us a lot of concern. The next, please. My presentation, after a short introductory remark, will describe the pond. Thereafter, we shall speak about geotechnical site characterization, first about subsoil, secondly about tailings. Here I would like to mention that when we approached in '92 this job, we were strongly concerned about the static or monotonic liquefaction of tailings, and we were not concerned, or very little concerned, about the foundation of this tailing dam. It turned opposite after 10 years or more of the work. We are now tremendously concerned about the foundation problem, and the tailings problem has been to large extent simplified and positively characterized. Thereafter, I shall show you some unsolved or partially unsolved geotechnical problem, and we shall go to the closing remarks. The next. The next. Next. This is a schematic of the mine. Here is the mine. Here is the superficial part of the mine. The ore extracted each year is 28 million ton per year. And obviously this is generating about 3% of waste. The production of mine is mostly related to copper and silver. There is some also some production of lead, and I even don't know what is this one. Probably the gold. But I am, unfortunately, I am not involved in this part of the problem. I am involved in the most dirty problem, which is the discharge of this waste into this huge tailing pond. In addition, the tailing pond is discharging every year between 5 million cubic meter and 21 million cubic meter of leachate from the pond into this river, which is the Odra River, is the second largest river in Poland. And because the environmental concern, but the plant cannot be stopped, this is the largest industry in Poland as the yearly turnover is concerned. They pay tremendous fines to the government discharging this leachate to the river. The next. This is the map of Poland. The Poland is located here, and the tailing pond is southwest part of the Poland, exactly in this point. This is the plan view of the tailing pond. You have two main decant pond and the secondary decant pond. This we will see later on. The next. The work is, the client is this Polish cuprum industry, which is the government industry. The government has majority the shares. The International Board of Experts is made of Dr. David Carrier from United States, Professor Richard Chandler from UK, Imperial College, Professor Kåre Heck from Oslo University and from Norwegian Geotechnical Institute, and by myself. We have as the interface, as the liaison officer with the client, the Polish geotechnical expert, which is Professor Wolski from Warsaw. When we have been appointed by the client in '92, as I have mentioned, they ask us for independent assessment of the following issues: stability of existing dam crest elevation plus 150, feasibility of dam crest increase in height to elevation 160, now we are about 167, feasibility of further dam crest rising to plus 200, re-evaluation of construction procedure and monitoring system, recommendation of additional soil investigation. And I shall mostly speak about site characterization, soil investigation. Next. This you see the board of experts, Professor Heck, Professor Chandler, Dr. Carrier, and myself. Next. Here's the Polish geotechnical expert, Professor Wolski. He is reading something, not sleeping, therefore his position must not be object of some insinuation. Next. The pond. Next. Here you have the fact files of the pond. The maximum height of the dam now above the original ground level is about 51 meters. The total volume of stored material is 372 million cubic meter. The storage rate is 70.5 million cubic meter annum. The area covered is 14.2 kilometers square. The dam perimeter is close to 15 kilometers, and the operation plant operation time is from 1977 to 235. It's clear that I shall not arrive to probably to see, for sure, to see this, the final stage of the construction. The next. The tailing is constructed using the worst, the most dangerous method, upstream method, as you can see here. Next. Here you see some pictures of the slurry pump out pipeline and the discharge of the slurry on the beaches. The next. This, unfortunately for us, this tailing pond is surrounded by a number of small towns and villages, which obviously has created tremendous concern about the public safety. Next. We can go, this is the environmental impact which this caused during construction, which I shall not discuss especially. This impact of the tailing pond surroundings is about 30 square kilometers, and the most important problems are contamination of surface and groundwater by infiltration of post-flotation leachate, dusting caused by wind on the beaches, the wind erosion, and this obviously is requiring continuous monitoring of groundwater, air, and terrain. As I mentioned, there is a discharge of post-flotation leachate into Odra River, which is ranging from 6 to 20 million cubic meter annum. Next. Here you can see the Żelazny Most environmental monitoring, which I cannot spend time on this. Everything is strongly monitored, including the problem of the population health. The next. Geotechnical site characterization. The next. Here we must stop for a while. You see a very young inventor. This is about 1979, and this is the invention. This is a dilatometer. This Professor Marchetti teaching the people at a very early stage of development of his baby in Singapore. And do you recognize in this young man this a little more aged man? Okay, the next. Site characterization, most recent investigation. The investigation focused on foundation soil, assessment of index and mechanical properties with special reference to Pliocene clay, which, as you will see, is critical for dam stability. Localization, description, and quantification of periglacial and glaciotectonics phenomena in clays, which are fundamental. And this was done, we are speaking about the most recent investigation, ordered and planned by us after 92, around 95, 96. And that is what we did as the most recent investigation. I must mention before going to the next slide that the area of the pond has been subject to 3 glaciation during the Pleistocene. And this glaciation create tremendous problems related to glacial tectonics, periglacial phenomena. I don't know if everybody is picking up these terms, and in few words is causing tremendous the presence of slickened sites, shear plains, even the hills of Pliocene clay, much older clay lying on Pleistocene material, and you will see partially this problem, weakening tremendously the clay. Next. Here we are starting to understand what is the foundation problem. This is the plan of the tailing pond. This is the ground level before the construction of tailing pond. This green area are represented the area in which the Pliocene clay, which you will see is very high plastic clay, tectonized tremendously, is lying over the Pleistocene quaternary deposit. Just to give you an idea, this is an example of relatively simple soil profile here, which is one of the critical section, 19 East. This is the Pliocene. This is the quaternary deposit. Just to give you an idea, you will see something which is even much worse. Next, this is the critical cross section to which I shall refer, 16 East. This is the dam at the elevation, at the present elevation, 165 or 66. This is the starter dam. This is the foundation. The red or light brown color is Pliocene, and light yellow color is Pleistocene. As you know, Pleistocene is much younger than the Pliocene. There are few millions of years of difference, and you see what the glaciotectonics create in this very complex foundation. Next. Tailings. For tailings, we concentrate on the evaluation of spatial variability of tailings, assessment of index and mechanical properties with special reference to undrained behavior in shear, critical for dam stability, location of phreatic line, and we did this different in-situ testing mostly, among which we have very recently performed 6 seismic dilatometer tests. We performed electrical resistivity CPTU, measuring both horizontal and vertical electrical resistivity, and we shall see some results of this test. The next. There is extensive, even if too chaotic, monitoring. This is the instruments installed in this tailing dam, just to think about 1,050 piezometers and 300 surface benchmarks and so on. Some very deep inclinometers going to the depth of 100 meters, and you will see very soon why. We have many information, but there is a complete lack of comprehensive database, and therefore to retrieve this information in real time from very chaotic documentation, mostly paper work, is becoming very difficult for us. And we are claiming from at least 5 years to give to somebody the task to prepare a database which can be read in real time and which can be accessed by the members of the international board. The next. This is the Casagrande plasticity chart, and we shall mostly concentrate on Pliocene clay because the quaternary deposits are sand and gravel, silty sand, which are not creating problem as the foundation is concerned. You see the Pliocene clay are very high plasticity clay, having the plasticity index which can go up to 80, 90, and ranging between 30, 35, and going to very high value. This is a typical grain size distribution, As you see, this is mostly clay, silty clay. Next, this is the over-consolidation ratio extended to the 60 meters below the original ground level. Clearly, this clay is over-consolidated by mechanical over-consolidation, and the pre-consolidation pressure is mostly giving you the idea about the highest glaciers which was present on this place, which was the second glaciation in Poland. Next, here you have some indication of peak angle of shearing resistance and effective stress cohesion intercept obtained from drain triaxial test on this clay. The drain triaxial tests are taking tremendous time on this high plasticity clay. And what is remarkable, you have very clear indication that as the plasticity index is increasing, the peak friction angle is decreasing to very small value at very high plasticity index. Moreover, the problem of determination of peak strength envelope here is also complicated by the presence of slicken side, which are obviously leading to the need of very large test for a given specimen in order to have some possibility to establish a reliable strength envelope. The next, these are the results of residual, the determination of residual strength of this high plasticity clay. The test has been done at Imperial College of London using ring shear apparatus. This is simply the tau shear stress over normal stress measured during two different ring shear tests, leading to this value of residual friction angle. Here you have the residual strength envelope from this test. The next. Can you go for just for a while to the previous one? Okay. Please note the extremely small rate of rotation which was necessary to assure the evaluation of drained residual strength to avoid any complication due to the pore pressure increase. The next. Here you have the same results. This is the residual friction angle at different normal effective stress, and what is also quite important, that as quite well known from previous investigation, for this high plasticity clay, the residual friction angle is decreasing as the normal stress is increasing. The friction angle is given here, and the normal stress is given between the parentheses. And this is also important feature because we are increasing continuously the normal stress, rising the dam, and the residual friction angle is going to some extent down. The next. The other very complicated feature of this foundation is that within deep Pliocene clay, we are finding slightly more pervious layers, mostly silt or slightly sandy silt, in which we are now finding the piezometric pressure, which is either artesian or subartesian, very close to the surface, rising from this elevation from very large depths. This must be compared to the piezometric head in quaternary deposit, which was always below the ground level, and therefore from the initial investigation performed before construction of the pond, never such high pore pressure has been found. The next, we have discovered this relatively recently, about 3 years ago, and we have a non-easy task to explain this, and we are making the investigation. There are potentially 3 possible phenomena might be involved. Seepage from the decant point, but this should be immediately confirmed by the chemistry of the pore water, which is not the case. Construction excess pore pressure in sealed, sand silt or brown, there's also brown coal at large depth lenses. And so far, no consolidation excess pore pressure has been recorded during the construction of the dam. Seepage from nearby higher ground, there is a lack of evidence that pore pressure prior to dam construction was truly artesian. And therefore, we are investigating this problem because, as you will see, we are facing for one or two dam sections the danger, the threat of very deep shear failure. Next, tailings. Here there are many surprises. The next. This is the typical range of grading for tailings. Here you have the typical sand fraction. L means lime silt fraction and clay fraction. Here you have the mineralogical composition, mostly quartz, as you see. The specific gravity is ranging within these two values. Next, crosshole. Here the complication started, especially with these waves which Dr. Foti likes a lot. Here you have two crossholes. These are the shear wave velocity, around 160, 200 meters per second. Roger, will you sign for me in order to be formal? Shear wave velocity, very regular, no problem, something which we expect. Here, have a look at the compression wave velocity. The compression wave velocity at these two locations is reflected very complicated situation regarding the phreatic line and the saturation line. I would like to mention, and you will see the example, that phreatic line is the line corresponding to zero piezometric head and is not coincident in general with the saturation line. These two lines can be quite different and only occasionally coincide. And you see that only at this depth we can speak about the full saturation because the compression waves are more or less constant in around 1,600 meters per second. Hence Professor Schmetner likes feet per second. You must multiply this by 3.3, more or less. And otherwise here is completely unsaturated material. Here is unsaturated, but here you have probably patched water table in the tailings, which is giving you some kind of saturation peak here. Very complicated situation. Obviously, you will see the evaluation of porosity of tailings was done only starting from this point, from point of full saturation. Next. Here you see the porosity evaluation. This is the porosity, the different dots are the porosity from two crossholes. One of these has been done, was certified by Dr. Foti, therefore you can believe in this data. Where is Dr. Foti? It's here. The other was done by me after the certification by Dr. Foti. You remember you sent me the email just before leaving to United States. And this line is the mean porosity for undisturbed samples, which are block samples retrieved from the tailings. And even if we don't have the absolute correspondence between location of the sampling and location of the crosshole, this is very good confirmation that what Dr. Foti showed us this afternoon. The next. Here you have an example that the piezometric surface or phreatic surface is not coincident with the full saturation. In this case, this is the shear wave velocity measured in 3 different cross hole. Here also we have measured the horizontally polarized and vertically polarized shear wave velocity in the cross hole using cross hole method, and I can assure you that also in this case the evaluation of porosity taking these 2 shear waves is leading you to very similar results as I have shown you for Chioggia, which is the Venice, just for understanding. Here you have the compression wave velocity, an example. You see, the saturation is clearly started here, but the piezometric level read in the 3 or 4 adjacent piezometers is giving you this level. There are many cases where the piezometric level is higher than the saturation line. There are also cases where the saturation line is higher than the piezometric level, especially if you are facing the problem of important capillarity rise. I cannot develop to larger extent this problem, but this is a quite important problem for liquefaction and for many other situations. Next. Now we are going to this recent baby of Silvano. This one you have seen. The next. These are 2 seismic dilatometer carried out close to the dam crest here and about 20 meters from the dam crest. You must understood that in tailings, because the method of disposal of the tailings close to the dam crest, you deposit more coarse material, sand. As you're going farther and farther from the dam crest, the material is becoming finer and finer. Even if here the distance is relatively small, you see that the red line is corresponding to the seismic dilatometer closer to the dam crest, the yellow farther from the dam crest, and without going to the details, you see that the constraint modulus, dilatometer constraint modulus, is higher closer to the dam crest, picking up clearly more sandy nature of the material, and this can be also found looking at the shear wave velocity. These tests were extremely successful. We ran 5 of these tests very recently at Żelazny Most, and the tests have been mentioned already before. The next. This I had a small discussion with the boss, with Silvano. I took 5 locations at which the seismic dilatometer has been performed. 3 of these locations I was, and I am directly involved professionally. Other 2 results was given me by Silvano, and I took the worst location of the shear wave velocity measurement. That means the worst location is for me the location at which 4, 5, or even 10 blows, like it's happened at Żelazny Most, gave the larger scatter of the results. Therefore, I am referring to the worst example of the repeatability of the seismic dilatometer, which is for geotechnical engineers is something unbelievable. And here you have the standard deviation in meters, which should be compared to the mean value of the shear wave velocity measured in meter. And here you have the covariance, which is the mean divided by the standard variation in percent. The only result, I must say that if you will take the book of Professor Haar giving the variation of soil properties for different parameters and for different soil, you will never find the variation or standard deviation less than 20–25%. Therefore, if you are speaking in geotechnical engineering about covariance of 6.3%, this is really nothing. But this is the worst example, and I know from Diego, he told me during the dinner, he was eating, but I was not eating, as you know, in order to keep you awake, that this was partially due to the noises, because these tests have been performed very close to very large electrical gas or oil-fired power plant, and this was causing the noises. I am right, Diego? Okay. And therefore, there is really unbelievable repeatability of this test. The next. We measure also the electrical resistivity using the electrical resistivity cone, allowing us to measure both the horizontal and electrical resistivity around the cone. This was done, the purpose of this test was twofold. The first, we have some idea about having an independent evaluation of the porosity. The other was that from some small interpretation of the electrical resistivity, you can obtain the information about the intrinsic or structural anisotropy as opposed to the stress-induced anisotropy, because what was the subject of presentation of Dr. Foti, he was speaking about the anisotropy, which is including two components, structural anisotropy and stress-induced or mechanical anisotropy. Hence we have also the horizontal and vertically polarized waves. We are very interested we are still interested to work out something about the anisotropy of tailings. The horizontal and electrical resistivity in ohms per meter times meter are shown here. We made the interpretation only starting from the point in which the tailings are starting from the point of the piezometric level, because in order to make the rational interpretation of this electrical resistivity, we need the electrical resistivity of the pore fluid, which is already a very complicating factor. And this resistivity of pore fluid, which is not constant with depth, is not constant in space, can be measured only when you are going into the saturated material. These are against two tests. One is run 40 meters from the dam crest, one 200 meters from the dam crest, and against these tests are reflecting the change in the grading as you are going farther and farther from the dam crest, where at the dam crest you have sand, and as you are going farther from the dam crest toward the decant pond, you are going into finer and finer material. Okay? The next, this is what we were using to interpret the electrical resistivity. We are mostly interested in deriving the porosity and to obtain the information about intrinsic or structural or fabric anisotropy, which is the ratio of formation factor. The formation factor is the measured electrical resistivity divided by the corresponding resistivity of pore fluid. And when the resistivity of pore fluid is not constant with depth, this is making this interpretation a little cumbersome. The next. Here you have the average formation factor, which against reflect not only the structural anisotropy, but is reflecting the grading of the soil. In fact, the average formation factor depends on the distance from the crest of the dam, against giving you some indication about the boundary between more sandy and more silty material. Here you have for comparison, you have the shear wave velocity measured at 3 distance from this is seismic cone, at 3 distance from the crest of the dam, and again you see that closer to the crest you have higher shear wave velocity, farther from the crest you have lower shear wave velocity. The next. The other tragedy for people which must thereafter to perform the design calculation, is the variation of the piezometric head in the tailings. The piezometric head in the tailings is extremely variable, is depending from day to day where you discharge the slurry, is depending how pervious is the original foundation soil, because if soil is pervious, there is a downward flow. Close to the dam is the horizontal flow toward the drain. This is a continuous concern when you need to perform the stability analysis. And this is just to give you an example. This is the piezometric head in the tailings and in the foundation at 100 meters from the dam crest and at 300 meters from the dam crest. This is really, from the design point of view, a very, very serious and very difficult problem to solve. The next, here we are going to something which was the largest surprise in our already 15 years work or 14 years work. This is a figure presented in '99 at the Torino conference on stress strain behavior of soil, and is showing a series of tests done in 1998 on the block samples retrieved from the tailings. Obviously, we were mostly interested in undrained behavior of the tailing. This is Keynote consolidated compression in loading undrained triaxial test on tailings. The blue line, here you have the stress, shear stress or maximum shear stress, axial strain relationship. Here you have the stress path in MIT plot, S and T. The blue line is representing the behavior of reconstituted tailings. This is the stress strain relationship. Clearly you have liquefaction. Here's the stress path. The red dots are representing the behavior of this material in undisturbed state. And as you see, the undisturbed material is going through the phase transformation and thereafter is dilating. And in order to be clear, obviously we first run the undisturbed test, thereafter we use the same material and we have reconstituted the specimen with the same void ratio, subjecting the specimen to the same consolidation stress and running the same triaxial test. And this was a very important surprise. There is also clear indication that G0 in undisturbed state, measured using Bender elements, is higher than G0 in reconstituted state, confirming that the undisturbed tailings, they have either a special structure, either very thin bonding due to the precipitation of salts which are in the pore fluid. We don't know exactly, but they have completely different behavior. I must mention that before running this test, we ran about 150 triaxial tests on tailings, reconstituted tailings, spending tremendous amount of money and arriving to tremendous concern about the static liquefaction. Once we decided to go to much more complicated undisturbed sampling, this problem practically disappeared, or in any case has been largely reduced. Next. But because this was so unexpected and was so strange, in 2004 we decided to repeat this exercise, taking again a large number of undisturbed samples. This time the test has been done in Poland, the previous tests have been done at NGI. And again you see the undisturbed samples, the red stress strain the red stress path exhibiting exactly the same behavior, phase transformation, dilatancy, and reconstituted specimen, against showing you the liquefaction. And against, in this case, even the ratio of G naught undisturbed over G naught reconstituted was even higher, between 165 and 240. This was very good news, and this clearly reduce our concern about static liquefaction to a very large extent. The next, there are some detailed results of the Bender elements and tests on reconstituted and undisturbed samples. The next, this is most important, the 2004 test. You see, this result you already know. This is undrained shear strength for undisturbed specimen measured at the phase transformation. It makes no sense to measure at failure, because with the dilatancy you are going to very high undrained strength. Normalize it with respect to mean effective stress. This is the same undrained strength for reconstituted specimen at steady state, at full liquefaction. You see, the difference from the design point of view is really unbelievably important, and this undisturbed test saved millions and millions of US dollars, not of zloty, which is the local currency, to the mine. The next. What we learned from the site characterization? We learned many things. The most important are here. Tailings in undisturbed state exhibit dilative behavior during shearing. High plasticity Pliocene clay has been subject during Pleistocene to intensive periglacial phenomena, suggesting the presence of shear planes and slickenite extending to a great depth. We found the slickenite at the depth around 80 meters below the ground level. Pore pressure within tailings exhibit large spatial variability, and generally distribution is not hydrostatic. The other problem which we will see, the mine is very close to the tailing pond, and as you know, there is absolutely aseismic region, but the mine activity is inducing the called mine-induced seismicity, and this is also of concern for this kind of structure. The horizontal peak ground acceleration caused by mine-induced seismicity varies between 0.092 G to 0.06 G. Generally, as you are closer to the mine, which is the west dam, the peak ground acceleration is higher. As you are going farther from the mining zone location, the peak ground acceleration is going down. The next, selected geotechnical problems. Next. As I mentioned, when we started to work, we envisaged the stability problem of these types. Tailings flow failure alone, as above triggered by foundation soil failure, and shear failure within the Pliocene clay. Now we are mostly concerned about the third type of instability. Here you have the possible behavior of tailings, shear stress, shear strain. Fortunately, we are in this case 1. Here you have the well-known behavior of high plasticity clay, peak, residual, and we are now coping with this serious problem of foundation instability. Next. What are the geotechnical challenges? Obviously, we have already said shear strength of tailings, potential for liquefaction, shear strength of high plasticity clay, and this all periglacial phenomena, pore pressure in foundation, mining-induced seismicity approaches to the stability analysis and related safety criteria. This we shall mention later on. Next, the problems. This is the most scaring problem to me in this section 16E, which is the one having very close to the surface the Pliocene clay, since 77, we observe the displacement, vertical, that means settlement, and horizontal displacement. On the vertical, the upper diagram is showing you the horizontal displacement in millimeters and time in years. The green line is representing this benchmark on the starter dam practically, and the red line is representing this benchmark on the original ground surface close to the toe of the dam. And as you see, since 8 years or 7 years ago, there was no concern, but obviously in this period the dam has been risen to a large extent. And in last 6 or 7 years, we started to monitor large and in increasing rate horizontal displacement of this benchmark, and also to some extent of this benchmark. And now, in end of 2005, we have here experienced the horizontal displacement, which is about 450 millimeters, which is a lot. Okay. There is the vertical settlement. Obviously, here the settlement is negligible. Here the settlement is also of the same order of magnitude, but we are not concerned about the vertical settlement. At some point here, we install very deep inclinometers. We had shallow inclinometers, which were not showing nothing special. We install very deep inclinometers, the next. And this is unfortunately what we discovered. We installed the inclinometers, one at the crest practically of the starter dam, this one, and one on the toe of the dam. And these inclinometers have been successfully installed only in April of 2004. And you see what we discovered. We discovered this is the elevation above mean sea level, because the inclinometers are placed at different elevation. And we discovered that in both inclinometers we have very clearly evidentiated shear plane at the elevation about 40 meters above mean sea level. You must remember that the dam is now at 165 meters above the mean sea level. The original ground elevation is around plus 115 meters above sea level, and this is very repeatable from this to this. And these probably are local perturbation, but we are obviously concerned about this and about this displacement. And we have in June very important meeting, because we must certainly adopt some remedial measures. This is obviously regarding only the section of the dam where the Pliocene clay is just beneath the dam or very close to the dam. Where the Pliocene clay is at large depth, nothing happened. And Professor Schmertmann told me before the lecture that with so long dam, it must be some section which has high probability to fail. This is John the section, unfortunately. The next, we have a problem given the stability analysis to compute at least the phreatic line. We are very conservative on the phreatic line, and we are making, with very few exceptions, the calculation assuming that the piezometric head is increasing linearly with depth in order to evaluate numerically, this is numerical finite element calculation, the phreatic line in different sections. We made some assumption how the coefficient of permeability change from the starter dam, 1.5 10 to minus 3. I'm speaking about meters per second because we have Professor Schmettmann yesterday told me about millimeters per second, and I was completely confused, John. And as you are going from the starter dam toward the decant point, obviously the soil is becoming finer and finer, and in the decant point we have the soil which is 4.2 times 10 to minus 9 millimeters per second. Therefore, the permeability decreases in this direction. The next. Here, what we obtain as the phreatic line for different cross-section for the design. The next. The design parameters. We have adopted, after 4 or 5 years of intensive soil investigation, the following design parameters for the stability analysis. First of all, there the shear strength of Pliocene clay, which is the real problem. We have some zone of a specially disturbed zone of salifluction. We have some cryoturbated zone, and finally we have tertiary clay, which is lichenite and contains a lot of shear planes. There are the design parameters adopted for Pliocene clay. For quaternary deposit, as you can see, at this shear strength, there is no problem with the stability. For the tailings, despite this experience with the undisturbed samples, we stay very conservative. We have, for upstream tailings, we have S U over sigma prime V 0.25, which is much lower than the same value at the phase transformation. And this part of tailing is fully drained because different toe drains and so on. For tailings, we have phi prime 34 degrees and C prime obviously 0. This is very close to the friction angle at critical state. The next. This is the input, seismic input for stability analysis design. This is the horizontal ground acceleration versus the dam cross section. As you see, the west dam has the highest peak ground acceleration due to the mining works. This is meters per second, 0.92 meters second square. And as you are going to other sections, this seismicity is attenuated, especially the section which is moving, which is 16E, this is the section of major concern, has a relatively small peak ground acceleration. This kind of very complicated seismicity investigation allow us to differentiate the seismic input along the perimeter of the dam. Next, as it should be, the vertical peak ground acceleration is much lower. I have no time, but this is the rule. I have no time to explain why. And again, this is showing the same trend with the going along the perimeter of the dam. The next, this is the for horizontal peak ground acceleration. This is probability of exceedance, and we are taking the probability of exceedance of 5%, which is here, and this probability of exceedance is corresponding to something, this no direct comparison for the earthquake-induced seismicity to the return period of about 470 or 450 years. But here this, to mention the return period has no sense except that we are using similar exceedance probability. The next, stability analysis. The stability analysis is currently done using Fredlund global limit equilibrium method and similar Morgenstern price method. There is a potential for extensive portion of non-planar failure surface has non-circular analysis. This is mostly due to these glaciotectonical phenomena. We are making always, except some specific cases, conservative assumption of hydrostatic pore pressure distribution below the phreatic surface, as long as this very conservative assumption is complying with the required pore pressure safety margin. If not, more detailed pore pressure analysis are required. The required safety factors are failure involving large volume of tailings, not considering the mining-induced seismicity must be 1.3 at least. When we are considering the mining-induced seismicity according to the Polish regulation, even using extremely conservative pseudostatic approach, we must stay above 1.15. This is causing us some problem. The next, this is one example of non-circular sliding surface at this critical dam cross section. We have 127 with the horizontal coefficient of acceleration equal to 0.04, which is too high if related to the distribution of P-ground acceleration around the perimeters. This analysis has been done before we obtained this beautiful data concerning the mining-induced seismicity. The next, here you have an example of different cross-section with the mining-induced seismicity and without mining-induced seismicity. And when we go, this is the case, below, this is unfortunately the East Dam, the one which is moving too much to too low safety factor with the induced seismicity. We are going to examine the local piezometers and the local ground water condition, which unfortunately are changing with time, because the tailing pond is a very strange geotechnical structure in which the boundary condition and initial condition are continuously changing with time. And in this case, taking appropriately the piezometric head, we obtain instead of 108, 1.21. All these stability analyses are not considering this very deep sliding or displacement surface which we have discovered recently. When you are making with the design parameters the calculation of stability for this deep sliding surface, you are ending with the safety factor which are higher. And we don't know exactly in what kind of soil and this sliding is occurring. We don't know what is the role of brown coal which we are finding in lenses at the same elevation, and this is the problem which we shall try to solve in the next future. The next, closing remarks. Next. As I have mentioned, the challenge is extremely complex geology and groundwater condition. Boundary and initial conditions are changing continuously. There is a serious environmental hazard, which I did not deal with, and this is mining-induced seismicity. As I have mentioned, we have considered different accident scenario, and however, owing this test on undisturbed samples, the hazard of liquefaction has been largely attenuated. Next. The other problem which became very important and very frightening is the instability of dams founded on high plasticity clay, interested by this extensive glacial tectonics periglacial phenomena. Recently we have the problem of this large, deeply seated horizontal displacement observed at two dams, east and north dams, which not by case are the dams where the Pliocene clay is very close to the dam. And in this situation, we clearly must raise the question to the client that it might be not feasible to raise the dam to elevation of 200 meters. It can be for some section of the dam where the Pliocene clay is close to the surface, it can be some kind of threshold shear stress, beyond which the shear strength of this highly tectonized, high plasticity clay is not able to withstand. One fortune is that in this clay, because we are very close to residual as the operational strength, the behavior is very ductile. Nothing can happen leading to very large displacement of the dam. And this is, to some extent, is probably our fortune. The next. Obviously, we are thinking about the remedial measures, which we have already adopted partially. We are thinking about stabilized berms, but don't forget that the stabilizing berms are of limited efficiency because very low residual strength and very low strength of the soil, and therefore even increasing to large extent the vertical or normal stress on the sliding surface, which is horizontal or subhorizontal, the benefit is not very large. Now we are making some tests with the very deep dewatering relay wells to relieve this high pore pressure which we found on these two sections which are subject to large displacement. And this looks as something which can be very efficient, and it will not cause tremendous problem to the mine because around the tailing pond we have already the relief wells which are pumping the leachate drain from the around the dam. That the problem of pumping out the water will be absolutely not aggravating the cost of running the tailings pond. What is important, we try, and we shall try in the future, some advanced numerical analysis, but with this special variability of, especially of foundation, but to some extent also of tailings, significant of any advanced numerical analysis is very questionable. You cannot reproduce the special variability of foundation soil which you have seen. Or if you will try, as we did something, you must simplify to a very large extent. Next. There are also some remedial measures on environmental impacts which I am not going to discuss here. Everybody who wants to have the copy of this presentation must ask Roger. I leave him free to release this presentation to everybody. The next, I must acknowledge the management of Żelazny Most copper mine for consenting me to present this lecture. I must express my special thanks to the friends and colleagues from International Board of Experts, Dr. Carrier, Professor Chandler, Professor Heck, for their high scientific expertise, dedication and competence, to Professor Wolski, Dr. Lipinski, Dr. Sorbian from Geotechnical, and to Professor Młynarek and Czuska. He's from Poznań University and he's running a company, HIBO, for providing the experimental data contents of this lecture. The next. Finally, I must acknowledge the many geotechnical consultants and many companies involved in this very huge work, which you can see here. They are mostly from Poland, but there is also ISMES from Bergamo, there is Imperial College from London, this Norwegian Geotechnical Institute, and there are many people which contribute and are contributing to this challenging work. Thank you for your attention. Question? Please come to the microphone because otherwise I must repeat your question to the audience.
Thank you. It's probably the influence of wine making me ask this question. I wasn't quite sure where the factor of safety requirement of 1.3 or 1.15 came from, whether that was...
1.3 is without seismicity induced by mining, and 1.15 is for including the mine-induced seismicity and using the pseudostatic analysis, which in my opinion is very conservative.
Yes, sorry, I wasn't quite sure. I understood whether it was imposed on the project or whatever.
This is Polish regulations.
With the uncertainties involved, I mean, what does that mean in terms of the likelihood of failure? Has anybody looked at it that way? That's my wine-induced
it
question.
was something was done in this condition. It is not very easy, and the likelihood of failure was 10 to minus 2.
I'm thinking about the effect of aging, because the dam is roughly 30 years old at the moment, and I understand there's another 30 years to go to get to that 200-meter elevation. Yeah. And the factor of safety is quite close to what's required. It's just a little bit shy for the east part of the dam. But also, when you modeled, when you did the reconstituted materials, you found the results were very different than the natural materials, the undisturbed material. And of course, there's a possibility that that is due to aging effects. Yeah. And I think the tailings itself is only going to themselves are only going to improve their properties with time. So have you considered, how will you consider the positive effects of, presumably positive effects of aging during the next 30 years to get you from 1.08 to 1.15?
This is a very good question, and it's also related to a very important Terzaghi lecture, which Professor Schmertmann presented how many years ago? 88? 89. I was very close. Because you remember you sent me the draft, which is almost a book about aging, and therefore I can answer the question. First of all, I must say that the undisturbed samples which we have retrieved from the pits excavated in the beach are not more than 5-6 years old, because we were not able to go, or we don't went deep. And therefore I am not sure if the real aging is, at least for these samples, is playing an important role. I believe that the difference between undisturbed and reconstituted specimen is mostly due to the structure. They are very elongated particles, and probably they are formed a very complicated structure which we don't know. And I expect also that because the leachate, because the pore fluid is the leachate, contains a lot of different minerals dissolved in the pore fluid, that it can be some precipitation and some very teeny bonding at contact between these very angular grains, obviously. On the other hand, we have some indication from the shear wave velocity and from some general information that tailings, indeed, deeper tailings, are subject to aging. And in fact, our next step will be to retrieve the undisturbed samples and to investigate in Keynote consolidated specimen in large 4-inch in diameter triaxial cell, the aging for a long duration test. But I am not able, I expect that it will be quite important aging, certainly much higher than we expect for clean quartz sand, which still is not negligible according to the Mesri data. Okay. Sorry, I would like to add one point which I mentioned to you yesterday. Our experience in Venice, in Ravenna, in many sites around Italy, is that the C sub alpha, the coefficient of secondary compression in undisturbed state for all natural material, and all natural material structure by definition is higher than the C sub alpha you measure in laboratory. And if this is also true for tailings, C alpha is higher than expected for this kind of grading, and the aging will be more important with time. This is what I expect.
This is not related to aging. What about the strain compatibility of the movements that are involved? Have you, no doubt you've thought about it, but you haven't said anything.
Yes, this question has been analyzed. At the beginning, we were concerned about very large fragility of tailings. Fragility, that means structural collapse and liquefaction. And this problem has been considered because this was a very large difference between the strain at which you start to liquefy the tailings in monotonic loading on reconstituted specimen and the mobilization of shear strength in the Pliocene clay. The quaternary sediments on other sites are of very small relevance, and therefore there was very large difference. Now, with this undisturbed behavior of tailings, this problem has been reduced to some extent, but still we consider the in fact, if you are looking at the design values of undrained strength, it is about 40% lower than the undrained strength inferred for phase transformation from undisturbed samples. To take into account this, obviously in an engineering manner.
I have a question with regard to the clay. Do you have an idea what type of mineralogy you have there, or?
We have the mineralogical composition of this clay. This is mostly elite, containing, however, sorry. We can speak Italian with Dr. Steiner. This is the dominant clay mineral is elite, but there are a non-negligible percentage of smectite, which is a very nasty mineral. Okay? Thank you very much for your attention.
Yeah, I was looking at it. 69 megabytes.